Namaskar and welcome to episode number 10 of Understanding Finance Physics podcast. When trying to understand something new, I want you to have the right attitude. When traversing through the unknown jungles, I want you to be sure of your footing. I want you to go at your own pace. I want you to. You are the one responsible for your understanding. We are all slaves to our understanding in a way. Unless we actually understand something, we cannot believe in it. We are helpless, right? So that's why going back to the first principles that you are definitely sure are right and you're comfortable with, and building up on that. And that is how your attitude should be. That is what your attitude should be. Like, if someone is telling you something and you find it complicated, I don't want you to think that it is because you are not smart enough to get that. It's just that the understand you are slave to your understanding. Something is not clicking in your mind. Some piece of the puzzle is missing, and what they are explaining to you does not contain that piece of puzzle. That's it. That's all it is. It's as much a problem of the way it is taught as the attitude of the person learning, right? And but it is your responsibility. If even if it's not your fault, it's your responsibility to pursue understanding. And this is where I want to start, because it's a tough journey. You will definitely come across things that do not make sense to you, and in those moments, if you can afford, step back and understand the reasons more deeply. I mean, especially in mathematics, we never are told as students that most of mathematics goes on from goes with this attitude of trying to invent something and then discovering what comes out of it, trying to establish some rules and some notation and some things, and then figure out what what comes next. So, for instance, here, in this chapter, yesterday's continuation, if you haven't listened to the yesterday's one, you won't probably understand this one, because it talks about the same big block of stone that is being heated from one position, let's say from bottom, right? And the heat is flowing through the stone from the bottom to the top, and there are these heat gradients. And this is a nice way to think of temperature field, which is the scalar field because it doesn't have a direction, and a heat flow vector field, the direction in which the heat is flowing in that big block of stone. At every point in the stone, there is a flow of heat which has some intensity and a direction. Okay, that constitutes a vector. And Feynman goes on to kind of make it a more formal and more precise definition of heat flow, which he calls H. The H is the name of the vector, and he says the magnitude of the vector heat flow at a point is the amount of thermal energy that passes per unit time per unit area through a very small surface element which is at right angles to the heat flow. That is the intensity of the heat flow vector. we are defining it like this: the amount of thermal energy in joules, I guess, thermal energy, the amount of it. Energy can be calculated by joules. The amount of that energy that passes in 1 unit time, whatever that unit be, it's up to us, a second, a minute, or whatever, through a surface, per unit surface, whatever unit we choose, through a perpendicular surface, a surface that is perpendicular to the heat flow, and that is the intensity of that heat vector at that point, and the direction is the direction of the heat flow. All right, so simple equation that comes up is H is equal to delta J. J is the joules energy, thermal energy. Delta means the change or flow, right? These terms are just man made. Don't worry about them. It's just a way to understand, just a way to formally put down things. Delta J means a change in J, change in thermal energy, and delta A is the small area that we are considering. So delta J divided by delta A times the vector, a unit vector. So what is unit vector, you might say? Unit vector is nothing but a way to give a scalar value a direction by multiplying both of them. It's like a unit vector. It's like just one unit. Okay, you give me 5. 5 is the intensity, but do you want a direction of that intensity? Yes, I'll give you the direction of the intensity. Here, take this unit vector in that same direction and just put them together, and then the 5 intensity that you have, the 5 number that you have, all of a sudden has a direction. That's it. That's a unit vector, right? In the direction of the heat flow. All right, so this is all is fine. You might be comfortable with this. Now he says that H can also be defined in other ways. What is that other way? Now here, that other way is a collection of its components. Okay, what does that mean? Let's say we have the heat flow in one direction, but we want to find out the heat flow in some other direction. How much heat is flowing in this direction? I don't care about the perpendicular direction. You know what I'm saying? Like, there is a heat flow straight. Let's say you are standing and you're looking at a wall. Heat is flowing from your eyes to the wall. That's the actual heat flow direction. Think of that direction, okay? Now, if you look up to the top of that wall, what's the heat flowing from your eyes? If there is heat flowing from your eyes, terrible example, but go with it. Heat flowing from your eyes to that top point on the wall, not straight on the wall, but up above there, up maybe 2 meters up. You might say, I mean, most of the heat is flowing. All the heat is flowing straight. So what part of that heat is flowing towards that point, the up there? And you say, okay, this is easy to find out because we have something called trigonometry, right? What is trigonometry? Let's say you don't know anything about trigonometry. Let's say you are the first person who comes across, you're just trying to understand your world, right? And you see that you make triangles. You're trying to understand abstract shapes, and you make triangles with one angle which is just 90 degrees, which is a lot of things in the world. You know this shape of this triangle, which is 90 degrees on one side, and then there is this angle Let's say you are working in a field, right? And you want, let's take an example. You're working in a field and you have a square field, but you want to know the distance between one point to the opposite point in that field. But you know the distance of the parameters, but you want to know how many seeds you want to spread if you want to make a line of trees from one point to the other point, and you want to know how to just figure out from the other values, and you realize that there is this harmony in the triangles that it depends on the angle itself. That's it. It just depends on the angle of your path across the field as to what the length of that path is, right? And you always figure out, okay, if I just know the angle and I know my the perimeter, I know the angle, I can figure it out without even actually measuring it, because it's always the same. And you say, okay, let me name it. Let me name that. So you can say only the ratios between the sides of a right angle triangle are always going to be this thing, and you name it sine theta, cos theta, tan theta. Sine theta is the angle between the opposite end and the field, and the path across the field. Cos theta is the ratio between the this side of the perimeter, your own side of the perimeter, and the path across the field. And tan theta is just your side of the perimeter to the opposite side, not the opposite, but the right angle side. You know what I'm talking about. I don't need to show you the picture here. Now, through you define that, you understand that, you get comfortable with that on your own terms, and you realize here also, when we are trying to understand heat, you can see that the direction of heat flow in the direction of our angle, which is theta, away from the heat flow, the actual heat flow, the heat flow h vector, the other side, sorry, the angle, the component of the heat flow that goes through that angle that you've chosen is cos theta times that thing. I think I'm making it really confusing. It's not that confusing actually. But it turns out that it's easy to now think of vectors as a collection of components, one in this direction, the other one perpendicular to this direction. Another thing that comes out of this discussion is the dot product of two matrices. The dot product, how do you think of a dot product between two matrices? How do you understand this new thing that you come across? Okay, you are told that there are these two vectors and there is this dot product. Well, the answer to the dot product is a scalar. It's a scalar. When you combine, it's essentially a way to combine the two vectors to get a scalar. But what does that scalar mean? Is again this same thing. Think of vectors. So if the vector is going in one direction, in let's say you make it on a paper, you make an x-axis, you make a y-axis, and then there is a vector going from the center of those the zero, the origin, to some angle, maybe 30 degrees with the x-axis and 60 degrees with the y-axis. Now you want to figure out every vector, this vector has some shadow falling on the x-axis and some shadow falling on the y-axis, right? Think of it as a shadow falling. What is the length of that shadow? If the light is coming perpendicular to the axis and casting a shadow, it will be the x component of that vector, right? And that will be x cos theta. Okay. And the y-axis of how long would that be? That would be not x cos theta, sorry, the length of the vector cos theta, right? Times cos theta. So the dot product is nothing but this shadow and the length of the shadow in the other direction times the other vectors. So I have a direct vector A in one direction and a vector B in another direction. If both are completely perpendicular to each other, the shadow is zero on one vector on the other, and in that case the dot product is zero, right? Because the shadow is zero. But if both are facing the same side in the same direction, the dot product is the maximum possible value, which is a times b times cos of 0. Cos of 0 is 1, which is a times b, which is just the product of two magnitudes of a and b. All right, so we got this idea that, okay, this is the dot product. Now coming back to the same problem that we started with, the component of that h, of that heat flow in our new direction up 2 meters up the wall, is h times cos of that angle that you are looking up the wall at. All right. And at the expense of making it too complicated, I think I'll stop here. At the expense, I meant to say, not to make it too complicated, I'll stop here. I'm all over the place today. I'm sorry. I'm gonna keep all this. I'm gonna keep this in the podcast and tell you how, and let you know how the sausage is made. This is how the actual understanding of my physics understanding goes. I am all stumped when I'm explaining something to someone because I'm never sure of myself. Anyway, we'll figure out some more things tomorrow and let this be chalked up as a bit of a confusing ending. But yeah, that's it. That's all I have to say today. See you tomorrow.